It's coming up. I'm just waiting on this thing to connect to my iPad. Come on. All right. So today we're going to be talking about, we're going to kind of switch topics, because we've been talking about kind of the precursors to all of the atomic and molecular stuff. We've been talking about compounds and elements and things like that. So now we're going to drill down a little bit deeper into that idea. We're going to talk about atoms and molecules. And within this subject area, we're also going to talk about physical and chemical properties, physical and chemical changes. We're going to talk some about the subatomic particles that make up the atom, and how atoms and matter are connected, right? All right, so let's think about what let me put the date in. Let's think about what the actual definition of an atom is, and then we're going to work from that definition and use that information to talk about the different properties of elements and compounds and the different changes that they undergo. So if we think about an atom, somebody help me with that. What is your definition? What do you think an atom is? Or if you've been reading through the chapter, you can answer that as well.
Cannot be destroyed. Is it something like?
Okay, so it can be decomposed. It takes a lot of energy, but I understand exactly what you're saying. It's like you can't do anything once you get something to the atomic level. You can't take it any further. Is that what you're trying to say?
Is it?
Yes, sir. Cannot be created nor destroyed.
Yeah, so atom, that's the smallest part of an element. So all elements are made up of atoms. So it's the smallest part of an element. Once you get an element, have an element, you can't necessarily break the element down so that it becomes something else. We talked about that already, but elements are composed of atoms, right? They have atomic particles that make them up. But if you take an atom of an element, it's still that element. It's not something, it doesn't become something else. If you have one atom or 100 atoms, you're not breaking that down into something else like you would if it was a compound. So when we have atoms, you can combine them, right? You can combine atoms chemically to get molecules. So let me give you an example. If I take a carbon atom and I add 4 hydrogen atoms, then I can add those atoms together to make CH4, which is methane, right? So I have ways that I can combine atoms to make molecules. All right, so you have atoms, you add them together. And this is balanced, by the way. We haven't done balancing yet, but if you count the atoms up on each side, there's 1 carbon on each side. There's four hydrogens on each side, right? So with the atoms, I can add atoms together to make molecules. Now let's talk about the atom itself for a second, because the model that we normally use is the Bohr model, right? And this is a preview of what we're going to be doing in chapter 2, but there's no time like the present. I don't like to, if we're discussing a particular topic, I don't want to make you wait another 3 weeks and then say, oh, by the way, this is what an atom is composed of, blah, blah, blah. I don't like doing that. I feel like if we're at a point where we can have a discussion, then we need to do it right then. So you know that the atom has 2 subatomic particles that make up the nucleus, right? One of them, let me just scroll in on that right quick. One of them is positive, one is neutral. This is a proton. We talked about this the other day, but redundancy in this case is good. This is a neutron. And then outside the nucleus, there's another subatomic particle outside the nucleus, and that is the electron. And this is negative. All right, let me do this. So it has a negative charge. All right. So can somebody tell me, looking at the atom and its composition, what do you think about the atom as far as like why they don't just randomly split apart? Like why don't people just randomly disintegrate? Because every human being is composed of different elements and different compounds that are made from atoms. So why don't atoms just randomly decompose? What do you think? What's holding it together?
The electron field, like the magnetic field.
Okay, so you're saying the electrons are, but what is okay, so I agree with that. But what is the electron attracted to even create the field around the atom?
Energy?
The proton, the positive charge of the proton.
The proton, right? The electron is negative, the proton is positive, they pull on each other, and that's what's holding that atom together, right? That attraction. Now, when you may have atoms with more electrons, as the electrons get further and further away from the nucleus, they become easier to ionize or easier to remove. But at its most basic level, the atom is held together by the attraction between the proton and the electron. It's a very strong attraction, by the way. It's very difficult to take an atom and split it up into its subatomic particles. It's possible, but it's not easy. All right. So when we think about the atom, it is the attraction between the proton and the electron that holds it together. This is my abbreviation for between. I'm an old school, so don't panic when you see that. It's just BWN for between. So the proton and the electron. Let me write that out. Sometimes you'll see me abbreviate electron as E minus. So that holds the atom together. Right? When we think about atoms, they are infinitesimally small. I mean, so small that the mass of a proton in the nucleus is about 1.7 times 10 to the minus 24 grams. Neutrons and protons weigh about the same amount, or have about the same. Let me not say weight. They have roughly the same mass, right? And the electron is even smaller and even lighter. This is 9.1 times 10 to the minus 28. Hold up. Grams, right? Very, very tiny, 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 tiny particles. Now, this might bring into perspective when we were talking about macro or micro. Like this is beyond micro, right? This is on a level that's, you know, basically undetectable without some really, really highly specialized and very sensitive equipment, right? So the atomic makeup, you have a proton, You have a neutron, and this is what we call the nucleus of the atom. And then you have electrons that orbit the nucleus. And the atomic number, as that changes, as the number of protons and electrons change, then so does the type of atom or element. All right. So these small particles make up elements, and they all have the same composition. They have a proton, a neutron, and an electron. And the more electrons you have, and the more protons you have, because they stay equivalent to keep atoms neutral, unless you have an ion. The more you have, that's how you generate different elements. I actually watched I took a class. It was like one of those free classes on Coursera that talked about elements and how they're formed. And the only difference is the atomic number, right? The number of electrons and protons. So when I thought about that, because we're used to seeing atoms, I said this earlier, represented a certain way. Like they might show you a block of aluminum, or they might show you, a black powder for carbon. But really the only difference is the number of electrons and protons. And that, the course that I took talked about how that process happens in stars, right? And so how certain elements that are on Earth are here because a star crashed into the Earth containing those elements. But those elements were created in a really chaotic, high energy process within a star, right? Excellent course to take, by the way. I might find the link and post it to Blackboard, but all of these elements come from really high energy processes where electrons are either added, electrons and protons are added or taken away. All right, so with the while we're discussing atoms, there are 7 atoms that actually exist as diatomics, and what we call, right? So diatomic atoms means that they exist as a molecule of 2 atoms together, right? So hydrogen is 1, nitrogen is 1, oxygen is 1. And then you have chlorine, bromine, this is Br2, and iodine, right? So when we look at hydrogen, if it's a diatomic, this is actually a molecule because it's more than 1 atom, right? And it's held together by a bond between the 2 hydrogens. So this is what we call sorry about that, covalent bond. I know we're throwing in some terms that are not supposed to be introduced yet, but we can introduce it. Y'all are smart, and it's going to click. Right, so that's what we call a covalent bond. That's a bond that is the result of shared electrons. Right, so a bond, so 2 atoms can share a pair of electrons and make what we call a covalent bond. And every covalent bond is the same. If I were to draw this a different way, I could draw a dot here and a dot here. Right, and then these 2 add together, and when they add together, that's when you get the covalent bond here. All right, so shared electrons make covalent bonds, and any atom bonded to another atom, if it's not bonded in an ionic fashion, it's bonded covalently. Right, so we think about, let me move this down, nitrogen and oxygen. I'm going to show you what those look like. Right, N2, nitrogen actually looks like this. So it's nitrogen. And we're going to talk about how to draw Lewis structures and all that stuff later. But there's no time like the present to introduce certain things, right? So this is what the molecular form of nitrogen looks like, since it's a diatomic. All right, it's still an element, but it exists as a molecule, right? So when we look at nitrogen, it has 3 bonds between the 2 atoms. So this is what we call a triple bond. All right. There are 3 covalent bonds between those 2 nitrogen atoms. And when we start drawing Lewis forms, I'll show you how that works, right? Because the way you know how many bonds to put is you have to know how many valence electrons are available, or how many electrons are in the outermost shell of an atom, right? And you can tell that by the group number on the periodic table. But I don't want to get too deep in the weeds, but again, you all are smart enough that we can bring up topics that we don't have to wait and then introduce something later, right? Oxygen is a little bit different. It is an oxygen atom, and it has what we call a double bond between 2 oxygens. So this is called a double bond. When we talk about later about hybridization and things like that, you'll learn that a double bond and a single bond are caused from different types of orbital overlap. But let me say this. Let me go ahead and say this too. That a covalent bond they result from orbital. I'm putting this in quotes. Overlap. So orbital is where electrons, that's where they live, right? We're going to learn about all that, shells and all. Some of you may already have some familiarity with shells and electron configuration and all that stuff, but we're just touching it now, but we'll see it more later. So these are your 7 diatomics, and these are molecules, right? So really, people had theorized or hypothesized about atoms and their structure, but we didn't really have a good understanding of this until right in the 1800s. When Dalton developed the theory for how the atom itself is, what the atom itself is composed of. So we didn't really have a lot of data to back up the hypothesis about atomic structure and the nature of elements being made up of atoms. We didn't have that until 1800s. All right. So with that being said, when we think about atoms, when atoms combine, they make molecules. So atoms they combine to make molecules. We already talked about hydrogen, H2. This is a molecule of hydrogen. Right? If we think about water, H2O, that's 2 hydrogen atoms bonded to an oxygen atom. It looks like this. Go ahead. Okay, all right, no problem, Brooklyn. Thank you. All right, so this is a molecule of water. All right, so atoms combine to make molecules. Atoms themselves are not necessarily molecular. They are the building blocks for elements, but some atoms do exist in molecular form, like hydrogen, nitrogen, and oxygen. But when we talk about a molecule, notice that this is a molecule of hydrogen. It's 2 of the same atoms. This is a molecule of water, and there are 2 different atoms that make that up. So molecules can contain the same atom, or they can contain multiple atoms that are different, right? So they can be made up of the same atoms or different atoms. All right. So now let's kind of shift gears a little bit, because now we want to talk about what all this stuff kind of means. And one of the places that you observe differences in atomic structure and molecular structure and all of that is when you start talking about the properties of certain elements or certain compounds. So now we're going to switch gears and start and talk some about physical and chemical properties. So let's do that. All right. And again, your properties are going to be based on the how atoms are arranged within an element or within a molecule, right? So your physical and chemical properties are going to have something to do with that. And it's not the composition, but how the atoms are arranged, because the composition is a little bit different from the arrangement. So the elements and the molecules that matter is composed of, how they're arranged, that's going to really account for the properties that you observe for that particular type of matter, right? So think about physical properties. Somebody help me right there. What is a physical property? What are we looking for?
The characteristic of a substance.
Okay, but what type of characteristics though? Think about it this way. Are you looking at macro characteristics or micro characteristics?
Macro.
Macro, right? Something tangible or visible that you can see with the naked eye. So a physical property is not associated with chemical composition.
So like a color.
Color, good. Tell me something else.
The hardness.
Hardness. What else? What about melting point, freezing point, boiling point? All of those are physical properties. So I'm going to say melting point, boiling point. I'm going to abbreviate point. Freezing point. All of these are.
about
Say that again. Okay, no mind. All right, freezing point. Do you think that smell is a physical property? I asked this earlier. Or is it a chemical property?
physical?
Okay, it is in a sense tangible in that you can detect it with your nose, but really the way something smells is literally based on what it's made of, like what's in it. So smell is actually the scent is a chemical signature, right? So when you detect something with your nose, that's because of whatever aroma is given off has a specific chemical makeup. So it's actually a chemical property. But we're gonna talk about that in a minute. So let's say when we're talking about physical properties of color, hardness, melting point, boiling point, freezing point, these are all associated with a particular type of matter. right? And then with physical properties, we can talk about different types of physical properties, right? Like extensive and intensive properties. So let me add a page here and we'll add that. Like physical properties can be extensive or intensive. So extensive or intensive. So extensive properties are based on quantity. So somebody give me an example of an extensive property. If I have more of it, then it changes. Give me an example of that. Let's say I have 300 marbles of the same composition versus 5 marbles. What's going to change if I put them on a balance?
They're gonna weigh different.
Yeah, so the mass is going to be different, right? So mass is an extensive property, right? It's based on the amount. The more you have, the greater the mass. The less you have, the lower the mass. Another extensive property is volume. If I have a gallon of milk versus a cup of milk, that's different. The volumes are going to be different because an extensive volume being a physical property, or the volume, as the volume changes, so does the amount, right? So this is quantity dependent. The same with length and width. All of these are extensive properties. They change. You can think of, if we have a brick, we have one brick that's going to you measure it across and you have a certain width. If you stack 6 bricks next to one another and measure that across, the width is going to be greater, right? So extensive properties are based on quantity. And then intensive properties right? These are independent of quantity. Right? Tell me something that you think when you think about something that where the quantity doesn't matter, a physical property where the quantity doesn't matter. I want you to think about this. What if I had a gallon of water and a cup of water, and I put it, we talked about this the other day, Thursday, I put it outside at 0 degrees. Does the freezing point change because I have more or less?
No.
No, that's an example of an intensive property. It's not dependent on quantity. So freezing point, boiling point, melting point, these are all intensive properties. Let me just put FP. Is that cool if I put it up here? If I put it up here? No, I didn't. So freezing point, boiling point, melting point, density. If I have a block of copper, if I have a 10-ton block, or if I have a 1-ton block, the density is still going to be the same. All right, I think it's 8 grams per cubic centimeter. If I have a gallon of water and I have 10 gallons of water, the density doesn't change, right? It's still going to be 1 gram per cubic centimeter. So the intensive properties are independent of how much you have. All right, and then if you take the ratio, this is another pretty cool feature about these extensive and intensive properties. If you take the ratio of two extensive properties, they give you an intensive property. And I'll give you an example. Right? If I take a ratio of the mass and the volume, right, I'm going to get density. Right? That's density itself is an intensive property, which is a ratio of these two extensive properties. All right. Any questions about physical properties, extensive properties, intensive properties, anything? All right. So with the physical properties, we know that there can also be, we're talking about physical properties. So we can also introduce the concept of a physical change, which means what? What is a physical change?
Is it anything that can be detected by your five senses?
Okay, okay. Well, we just mentioned that smell is chemical, but sometimes a physical change happens that may produce an odor. But a physical change happens when you take matter and you change its state or its form without changing its physical, its chemical composition. So it's a change in the state of matter, solid, liquid, or gas.
Is that just like frying the
Frying, say that again, frying an egg. Is that what you
Yes.
said? Actually, no. I know that it's tempting to see that because you can see a difference in the egg, but when you cook something, you actually alter the chemicals that that thing is made of. Because
So
eggs,
would it like,
say it again?
so would it be like pouring water in like another shaped glass or something like that?
Yes. If you took water and you poured it from a rectangular glass to a circular or cylindrical glass, yes.
What
Or-
about
Go ahead.
breaking glass? Like
Say that again?
dropping, like what about breaking glass, like dropping a plate on the floor and it
Excellent.
shatters?
Excellent, excellent. Yes, if you take a plate and you drop that plate on the floor and it's shattered into a million pieces, that is a physical change. All right. And even with that being said, if you put a plate in the microwave, that's a physical, when it heats up, that's a physical change because it doesn't change the composition of the plate. If you put styrofoam in the microwave and you heat it after over a certain period of time, that will end up being a chemical change because that styrofoam starts to decompose and degrade. Have you ever noticed that? That's why I stopped eating at American Deli, because they put hot food in the styrofoam plate, and that always causes the styrofoam to decompose. I don't want to eat that on my chicken. Well, I don't eat chicken wings, but when I order for my kids, I don't like, so I stopped ordering that. Because that styrofoam, when you overheat that, it does change like type. It goes from one type of matter to another, and you don't want that in your body. But so a physical change is a change in the state or form, but no change in the chemical composition. So it's like taking, it's like taking, if you took sand from the beach and you wet it, right? And on the one hand, it's granular. When it's dry, if you wet it, it becomes a little bit more compact and you can build a sand castle, right? That's a physical change. You haven't changed the composition of what sand is made of. You just changed its form by adding some water to it, right? By the same token, if I took a hamburger, let's say I bought a hamburger from Burger King. If I cut it in half, what type of change is that?
It's a physical change.
It's a physical change.
Physical.
I didn't change what the hamburger is made of. I didn't change the composition of the atoms of the bun. All I did was rearrange them physically, right? So with that being said, let's talk real quick. Let's take about 2 minutes. And let's talk about what a chemical change is, right? Because we can talk about chemical changes and chemical properties in the same breath. So let's introduce that topic and then we're gonna stop. So first of all, cooking produces a chemical change. I think we talked about this on the first day of class. Because when you can tell when some chemical has been altered because the smell changes. Right, so a chemical property is a property that is associated with what a specific type of matter is made of, right? So flammability, that's a chemical property. Toxicity, how it interacts with the cells in a living organism, that's a chemical property. If it's acidic or basic, those are chemical properties. How it reacts, the rate at which it reacts, that's a chemical property. So all of these are properties that are associated with the composition. Right? Remember, physical properties are not associated with how that matter is composed, but more so how it's arranged. This is the chemical properties are associated with the actual composition of the matter. All right. So think about this. Think about this in terms of when we think about chemical changes. When something undergoes a chemical change, it actually undergoes a change in its composition. Right? It undergoes a change in its composition. It's no longer what it was, right? So I gave an example this morning and we'll close out with this. How many of you have had lunch? You can unmute or you can raise your hand or let me look at the participants list. All right.
I had.
All right.
I had
What did you have? Who was the last person that spoke?
ramen noodles.
Ramen.
Me too.
Okay. Now, let me ask this question because this is a great example of what a chemical change is. That ramen that you ate, depending on your metabolism, whenever you get ready to expel that waste from your body that's going to come from that, is it going to come out looking like it went in?
No.
No, it doesn't. You know why? Because your body has chemically altered the ingredients in that ramen to convert it into something else, right? The enzymes in your stomach and in your intestines, the acids in your stomach, all of those chemicals act on whatever that food is made of to decompose it and then to take away the nutrients to give to whatever processes are happening in your body. So digestion itself is a chemical change, right? If you eat a hamburger, when you go and after time, when it gets ready to come out the other end, it's not going to come out looking like a hamburger. It's going to come out looking like mush, right? Because your body has broken it down. And your body has converted it so it can use it for energy, for protein with your muscles and your ligaments and all these other things, right? So a chemical change happens when matter changes type. So you start with one type of matter, but you end up with a different type of matter, right? And that's whatever the process is that causes that, that's causing a chemical change, right? So whatever you have for lunch, you're gonna see it later, but it's not gonna look like what you put into your mouth to eat. It's gonna look different because it's been chemically decomposed. All right, we're gonna stop right there. I said I was gonna stop early, but I didn't really stop as early as I had planned, but it's okay. Any questions before we adjourn?
No, sir.
No, sir. Thank
Hopefully-
you.
Hopefully this is engaging, staying interested to you. Feel free to ask questions and interrupt anytime during any lecture. So I'm gonna let y'all go. Have a good weekend. Stay safe. And we'll see you back on Wednesday, God willing.
Hey, I'm sorry. Did you take roll?
You can, I didn't ask for you to put your name in the chat, but I think I should be able to get the list of participants from Zoom because it records that automatically. So, but under normal circumstances, I would have asked you to put your name over there, but it's fine for today. There's no problem.
All right. You have a great weekend. Bye.
Okay, do the same.